On Monday, I said I was going to make a more in-depth video for talking about these error ideas, but the more I thought about it, the more I realized that it's really a matter of getting down into this nitty-gritty details that I don't think is really worth our time. So instead, I'm making this recap video, which is really just to highlight what I think are the important takeaways. So the general idea is that we have our null hypothesis, typically that nothing exciting is happening. The null hypothesis is either true or false, and wherever we are then going to either reject or fail to reject our null hypothesis when we run a hypothesis test. Some of the time, we will incorrectly reject or incorrectly fail to reject. We call these things type 1 and type 2 errors. As we said in class, the probability of rejecting the null hypothesis when we shouldn't have should be alpha. So this is the cutoff value for our hypothesis test. This is a value that we chose when we started setting up our hypothesis test. Naturally, it's nice for this to be a small value because that's going to minimize the probability of a type 1 error. That said, there are some trade-offs. So the probability of making a type 2 error, given that the null hypothesis is false, is this beta. And unlike alpha, which is some number that we just chose, beta is certainly more mysterious. Some other things go into the beta, like how close together are the things that we're trying to distinguish. But this is also influenced by things like alpha and our sample size. All right, so we have a name for this other probability. So if there's a probability of beta of making a type 2 error, then the probability of not making a type 2 error is 1 minus beta. This we're going to call the sensitivity of the test. If the null hypothesis is in fact wrong, this is how likely it is that we pick up on that fact, how sensitive our test is. So we also have a name for the converse for the alpha part. The 1 minus alpha branch is called the specificity of the test. This is the scenario where the null hypothesis is true, nothing exciting is going on, and we correctly come to the conclusion that, I don't think anything special is going on. That's the specificity. Now we naturally want both of these numbers, the sensitivity and the specificity, to be big numbers. We want the probability of making errors to be small. So how do we maximize the sensitivity and the specificity? Okay, so there's a bit of a trade-off. If we adjust this alpha value, as in if we change the threshold for rejecting the null hypothesis, in other words, if we decrease this alpha, we make it more difficult to reject the null hypothesis, then yes, that is going to decrease the probability of a type 1 error. However, it is also going to decrease the probability that we reject the null hypothesis in this scenario as well, which decreasing this scenario is going to increase this scenario. So if we decrease alpha, we increase beta, and vice versa works as well. Again, more things go into beta itself, namely how far apart are the properties we're trying to distinguish, but this is certainly a trend that happens. Again, we choose alpha, beta is a little bit more complicated. So while there is a trade-off between this specificity and sensitivity, there are some things that we can do to make this test just better in general, and that really boils down to increasing our sample size. If we increase our sample size, this is going to decrease our beta. This is going to increase our sensitivity. It's very difficult to distinguish between a coin that comes up heads 50% of the time and a coin that comes up heads 51% of the time. If we only flip 100 coins, there's a lot of overlap there. However, if we flip 1,000,000 or 1,000,000,000 or 1,000,000,000,000 coins, we might be able to start to distinguish between the two. We are increasing our sensitivity by increasing n. Increasing the sample size decreases beta. And the good thing here is that this is not going to adversely affect our alpha. Our alpha is sort of this independently chosen number, typically something like 0.05 or 0.01, and increasing sample size is not going to affect alpha. Okay, so the important takeaways from all of this, being able to distinguish between type 1 and type 2 errors, know this terminology, sensitivity, and specificity, and we want to have a general sense of how these values behave relative to each other. Decreasing alpha increases beta, vice versa, and increasing n is going to decrease beta, but not affect alpha.